All right, let's look at our graphs. So f of x is equal to 1/2 to the x. So remember that when this number is between 0 and 1, then this is going to be exponential decay, a decreasing function. When this number is greater than 1, it's going to be exponential growth, an increasing function. So like right here, this should be decreasing decay, and it is. This number is greater than 1, so it should be increasing and growth, and it is. We also said for exponential functions that you could count on 2 landmarks that you could use, and that is a y-intercept at 1 and a horizontal asymptote at 0. So for the parent function, the beginning function, if I know that it has the y-intercept at 1 and the horizontal asymptote at 0, and I know this basic shape of the function, then we said we could literally graph this exponential with 1 point. So I know what this piece of the graph is going to look like. It's going to approach that asymptote. So all I need to do is come over here and plug in 1 point. So like if I plug in -1, 1/2 to the -1 is going to give me +2. So that gives me my graph of my function. All right, let's look at the parent function over here. So for this one, we know it's increasing. So again, it's got that same y-intercept at 1, that same horizontal asymptote at 0. And I know it's got the increasing shape. So I know it's going to approach the asymptote here. I just need to plot 1 point over here to know how steep it is. So I'm going to plug in +1. And so 2 to the 1 is 2. And that lets me know how steep to draw it. All right. So that's my parent exponential function, both for increasing and decreasing, for growth and decay. So you'll notice that the domain, this is going to keep going this way, and this is going to keep going this way. So the domain is all real numbers. The range, if we start down here at the bottom, the first value that we come to is we're approaching 0. We don't equal it because there's an asymptote there, but 0 to infinity. So that's why we use a parenthesis with the 0. And I mentioned the horizontal asymptote at 0 and the intercept at 1. And you'll notice that these are all the same things again for that parent function. All right, so then for number 9, we asked you to take what you had just graphed in number 8 and change a few things to it. So any value subtracted from x is a horizontal shift. So 2 is being subtracted from x. Remember, we said you could think of it as the opposite of. This 1 is not stuck to the x. It could be moved to the other side and grouped with the y. If we subtracted 1 from both sides, that'd be y minus 1, and any value subtracted from y is a vertical shift. So what's being subtracted from 1 in y minus 1 is a +1. So if you don't want to move it over here with the y, you leave it over here, then you don't do the opposite of that number. So my horizontal shift would be 2, and my vertical shift would be 1. So I'm going to take those same points that I used to graph my pink function, and I'm going to use them to graph my new function. All right, so this asymptote, this intercept right here, I'm going to horizontally shift it a +2 and vertically shift it a +1, and there's that point right there. This point we plotted, horizontally shifted a +2, vertically shifted a +1, and there's that point. And then my asymptote that was down here at 0, if I move forward 2, it's still just a horizontal line, but then I go up 1, then my new asymptote would be here. So with those 2 points in my asymptote, then again, I can draw my new graph. So my domain is still all real numbers, but notice now that when I start from the bottom and come up, the first y value that I get to is 1 instead of 0. I have an asymptote at 1 now. And your asymptote and your vertical shift are the same for both of these. All right, so then if we take the exponential growth, the increasing function, and for this one, we have a horizontal shift again of opposite of +3, so -3. We have a vertical shift again of a -4. And then we have a negative out in front of the entire function, and that causes a reflection in the x-axis. So remember, the order that we need to follow is horizontally shift, and then reflect, and then vertically shift. So again, I'm going to take this original graph that I had, and so, for instance, this point right here, I can horizontally shift it 1, 2, 3. And then I can take that point and reflect it in the x-axis. So it's like if this is wet paint and I fold this on the x-axis, then it's going to end up right here. And then I'm going to vertically shift it down 4. So 1, 2, 3, 4. So there's that point right there. All right, same thing with this one. I'm going to horizontally shift 1, 2, 3, and then I'm going to reflect it. So right now I'm 2 above. So if I reflect it, I'm going to be 2 below. And then vertically shift 1, 2, 3, 4. So that's that point right there. And then for my asymptote, if I horizontally shifted a -3, that doesn't change because it's a horizontal line. But, and if I reflect that, it doesn't go anywhere, because if you reflect something that is the x-axis and the x-axis, it's the same. And so then I would just vertically shift it 1, 2, 3, 4. And so my asymptote would be at y equals -4. My range would be from -infinity to -4, and my domain would still be all real numbers. All right, then for number 12, they didn't ask me to draw e to the x, but I did just so we would have it as a reference. So if I want to graph y equals e to the x, remember we said up here that if you had a number that was greater than 1, it would have this shape, right? Well, e is 2.78, so that's a number greater than 1, so it's going to have that exact same shape. So again, you can see I've got the y-intercept at 1, I've got the horizontal asymptote at 0, and then if I plug in x equals 1, then I'm going to get e, which is 2.7. So when x is equal to 1, then I'm going to get like 2.7. And so that would be the only point I need to then be able to sketch my natural exponential function. All right, what they did though is they put a negative in front of the x. So when you put a negative out in front of the whole function, that's reflection in the x-axis. But when you put a negative just in front of the x and plug it into the function, that's reflection in the y-axis. And so we're going to take this original function e to the x and we're going to reflect it in the y-axis. So that's like if this was in wet paint and I folded it on this axis right here, then it would transfer right over here. All right, so looking at our pink function right here, you can see our domain is -infinity to infinity. Our range is 0 to infinity. Our horizontal asymptote is at y is equal to 0, and our intercept is at 0, 1. All right, then let's look at a logarithmic function. So exponentials and logarithmics are inverses of each other. And so if we look at the family or the parent function here, log base 5 of x, if I've got y equals log base 5 of x, usually we like to switch our logs to exponentials. So that would be 5 to the y equals x. All right, so if I have 5 to the y is equal to x, because exponentials and logarithmics are inverses, if I know that the exponential function has an intercept at 0, 1, then for its inverse, the logarithmic, it's going to have an inverse at 1, 0. If I know that the horizontal asymptote is at y equals 0, then on the inverse, it would be a vertical asymptote at x equals 0. So we said that just like you could graph an exponential with just 1 point, you could graph a logarithmic with just 1 point if you knew those two landmarks. If you knew that the logarithmic was going to have an x-intercept at 1 and a vertical asymptote at 0, so I already know what this piece of the graph is going to look like. It's going to approach that asymptote. So the only thing I don't know is how steep to make this over here, and so I need to just plot 1 point to find that. And it's actually easier to plug in a y value than it is an x value. So like if I plug in 1 for y, I get 5 for x, so that would be the 0.51. So right here, that's the 0.51. So there is my logarithmic function. You can graph any log function that way as your parent function. And you'll notice that for your domain, as we start over here, the first value we come to is 0 and we go to infinity. We're not equal to 0, so we put a parenthesis with that. The range, this is going to keep going down this way and it's going to keep going up this way, so its range is all real numbers. And we've already said we have a vertical asymptote at x equals 0 and an intercept at 1, 0. Something else that we also pointed out is because exponentials and logarithmics are inverses of each other, notice that the domain here is the same as the range here, and the domain here is the same as the range here. And as we said, x and y switched places, and x and y switched places. Now, when you give me the horizontal or the vertical asymptote, be sure that you tell me whether it's x equals or y equals. You can't just tell me 0 or you'll lose partial credit. All right, so now that we have our parent function, now you'll notice any value subtracted from x, we have a horizontal shift of 3. And then any value subtracted from y, if we move that to the other side, it would be y plus 2. So that's a vertical shift of -2. And again, if you don't want to move it, if you want to look at it on this side, then don't do the opposite of that number. All right, so we're going to take those same 3 points the same 3 things that I used a second ago to graph this. And I'm going to horizontally and vertically shift them. So this point right here, if I horizontally shift that 1, 2, 3, and then vertically shift it a -2, there's that point. And then this guy, horizontally shift 1, 2, 3, and vertically shift down 2, there's that one. And then this asymptote, if I horizontally shift it 1, 2, 3, doesn't matter if I vertically shift it, it's already a vertical line. And so there would be my asymptote. So I'm going to have an asymptote at x is equal to 3. My domain, if you start over here, the first value that we get is 3. We're not equal to it, but we're going right up to it at that asymptote. So 3 to infinity. And then this goes to -infinity and this goes to positive infinity. So our range is going to be all real numbers. All right, then for number 15, instead of making us graph it, they just ask us to identify the things that have been done to that equation. All right, so our parent function is just the 2 to the x. So the same type of thing we were talking about right up here. This is the parent function, and then they had caused a reflection and a horizontal shift and vertical shift. Same thing down here. They're just not asking me to actually graph it. They're just asking me to identify what those transformations are. So a negative out in front of the entire function is reflection in the x-axis. If the negative was just in front of x, that would be reflection in y. And then any value subtracted from x is horizontal shift, so opposite of that number. And any value subtracted from y, so since it's leaving it on this side, then it's not going to be the opposite. It's just going to be that number as it is. So that would mean that we had a horizontal shift of -3, so that's 3 units to the left. And then we reflected it in the x-axis, and then we had a vertical shift of -4, so that means we went down 4. So those would be the transformations that were performed on the original parent function. All right, then for 16 and 17, we're switching back and forth from logarithmic and exponential forms. So remember, you're going to take your base to your answer, and that's equal to what you were taking the log of. So 8 to the second equals 64. If we're going the opposite way, then again, this is my base, this is my answer, and then this is what I'm taking the log of. And again, you can check it. 3 to the 4 is equal to 81. All right, then starting with number 18, we're evaluating logarithms. So most of us don't like logs, and the first thing we want to do is get rid of them. So let's switch every one of these logs to their exponential form. So if I switch this to an exponential form, that would be 4 to the x is equal to 64. Now I want to get my bases the same, because if my bases are the same, then I'll be able to just set my exponents equal to each other. So I want to rewrite 64 as 4 to the something. So you can use your little calculator and say 4 times 4 is what? 16 times 4 is what? 64. And so I can say, okay, 64 is just 4 cubed. So now my base 4 is the same. So if this says 4 to the x equals 4 to the 3, since the 4's are the same and I'm being told it's equal, that means my exponents are the same. So that's where we get that rule that when your bases are the same, you can set your exponents equal to each other, and that would be our answer, x is equal to 3. All right, same thing for this next guy. I'm going to do 6 to the x is equal to 216. So I need to rewrite 216 with a base of 6. And so I can, in my calculator, say 6 times 6 is 36, times 6 is 216, so it's 6 cubed. So now my bases are the same. I can set my exponents equal to each other, and I'll get x is equal to 3.